We had a meeting with the visiting committee today. Many of you, some of you were there. And I should say that the committee was very impressed. This is a committee that visits the astronomy department once every 6 years. And they monitor whether things are going well, what is happening with the astronomy department, and also the higher administration at Harvard. So we channel complaints through the committee. It doesn't matter, it doesn't change anything. But it's a way of therapy. It's a form of therapy for the faculty. Let's put it this way. But they came here and they didn't anticipate much.
You can keep a seat for me.
It's okay, go ahead.
It's okay.
It's yours. Ramesh, at this point, it'd be easier for you to take this.
No. That's not my jacket.
I was just talking about the visiting committee, and Ramesh had lunch with them at the CFA, so he just came here. And they were very impressed. And they didn't. At first, they asked me why should they walk the distance, which is a 5-minute walk, because they said why don't the BHI people go there to meet with them? And I said that it's worth it, and they came here and they were very impressed by first that it's interdisciplinary, that we have people from different disciplines coming together and speaking to each other in the language that each community understands, which is English. And then, more interestingly, is the fact that we were funded and that we have an idea for how to continue this. And this is really unusual. You don't see people from the humanities together with science. People very often in a center. So altogether, I think they will probably say very good things about the BHI in their report. There was even a venture capitalist among them from the board of overseers, and she said that we should think about the BHI as a startup, because we started with an idea. We were not funded in perpetuity, and if we are attempting to get funded, we shouldn't think that we will get endowed, but basically, just like a startup, the idea works, and we demonstrate that we have a lot of activity and interesting results. We get a shadow of a black hole. We'll solve the information paradox. And the point is that we can get funded 3 years at a time, just like a startup at this point. Hopefully, someone generous will give us more in the distant future. But that was the suggestion by the venture capitalist in the group. So we should consider that.
Was he offering to fund us?
No, it was a she. By the way, you had an 80% chance of being wrong by saying he, because it was 4 out of the 5 members of the committee were women, which is actually, I was very happy about it. I wish all of them were in our department, actually. So anyway, we'll start with the colloquium today. Thank you all for coming.
So I just want to very quickly remind people of the format. We have 3 speakers today. The first is our physics speaker, second is philosophy speaker, third is astronomy speaker, so we have a very nice broad spectrum. The first 2 colloquia will be half an hour each, the third one, and that includes questions as well. The last one will be 15 minutes. And I'll hand over to Sasha.
Yeah, well, we are very happy to have Gaston with us today, visiting us from Buenos Aires, and Brandeis here, and he will tell us about stringy horizons and duality.
Okay, thank you very much. Especially thanks Sasha for inviting me to talk about this particular work I have done recently, which is at the same time based on a series of work done by Gideon Itzhaki and Kutasov, people from Tel Aviv, Jerusalem, and Chicago. So the main idea I want to discuss, at least in a very concise and somehow limited but precise setup, is this general question: is how a string sees a black hole horizon. In a very precise setup, which is under control for string theory purpose, but this is the general question I want to raise. So to be a little bit more precise, is the question I want to discuss is in how many ways a string state, especially at very high energy, sees the black hole, the structure of the black hole horizon. And this is especially important in the case of strings because strings have a very particular property, which is duality, and this is the one I will focus on mostly. So, okay, string theory is a theory of an extended fundamental objects. I mean, not only fundamental objects, because there are also higher dimensional objects, not only the strings themselves, which are the so-called Libranes, which appear as a non-perturbative states of the theory. But strings themselves, the fundamental object of the theory, the perturbative version of the theory, are extended objects, and somehow, this is a little bit roughly speaking, but it's fair to say that they probe the space-time in a different way, which is a kind of non-local. Okay? And the fact that, for instance, interactions between the strings doesn't happen at a very particular point, but they're different, like in a string of points, is at the very root of the reason why the string theory is consistent, especially at very high energy, unlike particle physics in some scenarios. But another very important property that derives from the fact that the strings are extended objects, and the fact that they probe, they explore the space-time, the geometry of the space-time in different manners, in this non-local-like manner, is the fact that strings see two field configurations, two backgrounds, that a priori seem to be different, they see them in the same way. This is what is called duality. And then I will focus on this. This will be an important part of this is the main idea I want to discuss here. This duality symmetry is, again, this lack of sensitivity of the strings to perceive as different two configurations that are seemingly different, but the strings see the same. So this is very nice because sometimes you are interested in solving one particular problem, and since you know that mathematically for string theory, the other problem that look like very different for the strings is the same, sometimes it's easy to solve, and then you can solve the problem you're interested in. Especially we will focus on something that is called T-duality. T-duality is one of the most interesting ones, and let me start with the antonomastic example of that, which is the fact that just to give a concrete example of what I mean when I say that the strings probe the space-time that are seemingly different background configurations in a simple manner. For instance, this is the typical example. It's like strings. Well, you know, string theory predicts that the universe doesn't have 10 4 space-time dimensions, but 10 space-time dimensions, and some of them have to be compact. So a string moving around with certain momentum around the compact direction is exactly equivalent from the string point of view to a string that is actually winding instead of moving in a radius which is 1 over the previous radius. Okay? There's some scale here that I'm missing, but basically it's a string moving around a small cylinder is the same from a string theory point of view that the string winding around a big cylinder. Okay? This is just an example of how different those two configurations can seem to be, but for a string point of view it's exactly the same. Related to that, not evidently related to that, but I mean it's related to that, is the fact that sometimes strings perceive gravity, and in other configuration they can feel some kind of B field, like a magnetic field. It's not a standard magnetic field. It's a magnetic field to which only the strings, not particles, coupled. But they can feel the same if they are under the influence of gravity or under the influence of this magnetic field. There is a map between one configuration and another configuration. This can be puzzling from the point at the beginning conceptually, because we know that gravity is geometry. So what does it mean? That sometimes gravity, which is geometry of the space-time, can be, if you will, mimic by putting a magnetic field or a different geometry and magnetic field. So this invites us at least to think of the possibility of including this B field as part of a generalized notion of geometry. And this gave rise to a very interesting formal development. The most important ones are generalized geometry and double field theory, in which indeed are frameworks in which you can incorporate the gravity, as we know it, and this magnetic field as part of a bigger geometrical entity. But I will not talk about this formal development. I will use this notion of duality to talk, as I mentioned before, about how strings can perceive, especially very high energy, in a different way, the structure of the horizon. Okay? Sometimes, you know, you have a geometry here given by the black hole horizon, the gravitational field of the black hole, and then you can map this to a different geometry, what is not necessarily a horizon there, and understand the things in the second picture. So let me start by just introducing, I'm sorry for those that are familiar with string theory, let me just mention very briefly what string theory is. This is a particle. We know that particles propagate in space-time, just following the word line of the particle, which is an its action in a very particular gauge, in the gauge in which the length, the geodesic length is parameterized by the proper time of the particle. This is the action of the particle in space-time, where this is the mass of the particle. So in a very particular gauge as well, the notion of the string theory is a natural generalization of this. This is the generalization, where now the string, when it propagates in the space-time, instead of a word line, it draws this word sheet, and the two coordinates tau and sigma are the one that parameterize this word sheet, right? So this seed coordinate now is the one that appears in the action. So this is exactly the natural generalization of a particle, a relativistic particle in a gravitational field given by this metric G linear. And this is not the mass, it's the tension of a string. Okay? This is the tension of string theory. This is a fundamental dimensionful quantity in the theory. Okay? So very large K means very large tension is the limit in which we should recover particle physics, where the strings becomes very, very rigid, but if you want the inverse is the length, so the string becomes very, very small. So remarkably, string theory, unlike particles, strings are a little bit reluctant to be formulated on whatever geometry you want to formulate the theory. So if you want the strings, to say it in a way, establish a kind of conversation with the background on which you want to propagate. There is some consistency conditions that the background has to satisfy for the string theory to be formulated there to be consistent. But remarkably, it is known that a particular example, and this is why I say that I will consider a very particular setup in which things are under control. I will consider a two-dimensional black hole. This is to say I will consider only the radial direction and the time. So 1 + 1 dimensional space-time. So if you want, it's a black segment. It's not the only background in which you can do string theory, taking into account alpha prime examples. Also, in 2 + 1 you can do it. But this is very interesting example to discuss the theory. Remarkably, this consistency condition that the background has to satisfy for string theory formulating on it to be consistent is given by a two-dimensional black hole. This is the metric of two-dimensional black hole. If you want, I'm putting the mass of the black hole to 1, so I'm setting these units here. This is the radial and time part of the metric of a Schwarzschild black hole in the cross-cut Finkelstein confidence. So indeed, this metric, this two-dimensional part of the metric, if you want, this is like a Schwarzschild black hole. The only thing is that it lags from the angular directions, right? So this is the standard diagram for a black hole. You have the future horizon here and the past horizon. This is the exterior of the black hole, and this is the interior of the black hole, and then you reach the singularity. So if you want this black hole, even though it's a two-dimensional, only the radial and the time directions are pretty much are reminiscent of a real black hole, Schwarzschild black hole. So this is the physical part, if you want. You have the exterior and the interior, and then you have the singularity. I will not enter into discussion whether you can extend this or not. I mean, it's very interesting, the extension in particular in 1 + 1 dimension, but I will focus on this exterior part. So if you change the variables in this way, R will be a radial coordinate for me, but in a very funny radial coordinate, R = 0 will correspond to the horizon. Okay? It's just a particular choice of coordinates I use. And if you make this change of coordinates, you can see that the metric takes this form. It's very simple to see. And as usual, when you are interested in field theory or string theory in backgrounds at finite temperature, and black holes are an example of that, you work in Euclidean format. It's not the only context in which you work in Euclidean formats, of course, but in gravity, well, okay, there is a discussion about that, because the need for which you need Euclidean formats in gravity is different from the rest of quantum theory. But we will work in the Euclidean formats, namely. We'll make this weak rotation, we'll think an imaginary time, we will call x, and then we will identify periodically the time. This is the standard technique to compute things when we are in quantum theories in presence of black holes. Of course, if you do this, the only thing is that there is an I square here, so this changes the sign. So this is the metric of the Euclidean black hole. If you think this metric, suppose you go very far from the black hole, like R is very, 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 very big, so this tends to 1, so it looks like a cylinder, because again, I'm making this rotation in time, but I'm identifying the time periodically. So this looks like a cylinder. You have a 1 here, and this is the metric of a cylinder. But if you go very close to the horizon, namely to r equals 0, you have a plane, because this goes like r squared, and this is the metric of the plane. The interpolating geometry is this geometry. This is called this is called sometimes the Witten semi-infinite cigar. It wouldn't be the Lacanian interpretation of it, but this is the, I will refer to this as the cigar, or if you want, to the Euclidean black hole. So just to be a little more precise, r equals 0 corresponds to the horizon, and here is mapped in this Euclidean picture to the tip of the cigar, which is smooth. So the interior of the black, it doesn't appear here. Okay? The interior of the black hole is south of the geometry, and this is important point. So the radial direction is given from the horizon to infinity. So, and this periodic direction is the time. So this is the asymptotic region, and this we can call the atmosphere. Okay, it's where the geometry is curved and is concentrated. The curvature of the manifold is concentrated close to the black hole. So you can think of string states in this black hole. In particular, you will see later. This is a little bit, if you want, a little bit sketchy, because if you think this is the time, so what does it mean to just to make a drawing of a string here? No? Because what does it mean? It's localized in time or whatever. This is a little bit sketchy. If you want, there is an alternative way of understanding this. It's just thinking, instead of thinking that this is a Euclidean black hole, namely I have artificially identified the time, I can think of this as a two-dimensional real Euclidean manifold and put the time as an exterior coordinate. This is a different problem, but it's very interesting in string theory because it's more related to, for instance, the description of strings in anti-de Sitter, three-dimensional anti-de Sitter space. Unfortunately, I will not have time to talk about that, but this is actually the real motivation I have to study these things. But there is a picture in what you can think of as time passes. You can think of string moving there if you want. But let me just focus on the interpretation of this manifold as a Euclidean version of two-dimensional black hole.
So, quick question.
Yes.
When you introduced the string action, you
Yes.
had a sigma coordinate.
Yes,
The tau and the sigma.
yeah, two and the sigma.
Is sigma external
No,
to these two,
no,
or
no.
is sigma is tau?
No, indeed, yeah. There are two-dimensional space-time here, and can be a little bit confusing. You have, if you want, the sigma is the one to parameterize the length of the string themselves, but the strings are posed on a two-dimensional space-time, and these are the space-time coordinates.
Okay, so
Okay.
it lives in this space, and
Yeah.
the sigma is just measuring
exactly.
length along the
Yeah,
space.
if you want, it's the difference as having a particle when you have a time direction, but also it's the tau is the proper time.
Thank you.
I'm a little confused when you're talking about the curvature here near the horizon.
Yeah.
But you're in a two-dimensional space-time. All two-dimensional space-times are conformally flat. There's no reaching curvature because
Yeah.
there's no
No,
matter.
your first affirmation is true. That your second is wrong. It's true that all space-times are conformally locally equivalent to a flat space-time, but it doesn't mean that the reaching curvature is zero. This is wrong.
That means that there's matter then.
No. Yeah. There is. It means that there is matter. Let me talk about that exactly. As the speaker 2 weeks ago said, this is a very important question because you know it was a joke. So as you point out, I talk about curvature. Indeed, even though this looks like a two-dimensional section of a Schwarzschild black hole, this is not Ricci flat. Which in 2 dimensions means it has no curvature because there is no difference between Ricci curvature and Ricci tensor in 2 dimensions because Einstein equations are trivially satisfied. So this can be puzzling at the beginning because you see one of the consistency conditions that the string the background has to satisfy for the string to be consistent formulated on it is the fact that they have to look like it has to be satisfy the Einstein equation. But this is only when there are no matter. And string theory. So just for this to be a solution of string theory, you need to add matter. Unfortunately, the additional matter that in string theory appears, one is the so-called dilaton field, which is a scalar field that the string theory always has, allows you to source the Ricci flat in such a way that this even though it has a curvature, is a solution of the field. But then you have to modify the action of the string theory in a way that is pretty well known and consistent with the loop at 1. Okay. And this is string theory. You are totally right. You have to add matter, and the funny thing is that it's still non-trivial that the matter you have to add is the matter that string theory predicts it has. As it's a dilaton field. So, okay, more than that, this is a perturbative equation, but it has been proven, notably by Witten, that because he gave the final proof of that indeed this is a solution at all orders in alpha prime, not only at first order in alpha prime. So this is a consistent solution of string theory. So But I will use this, instead of using these radial coordinates, since I have to introduce matter, as you say, the funny thing is that phi is proportional to this funny combination. Okay? So I will define this funny combination as little phi, just for convenience. So phi, big phi, the dilaton field, is linear in this new coordinate phi. So this, I will use this coordinate phi, and also I will, as I mentioned before, I will put x as the name for imaginary time. For the concerns, for those that are familiarized with this can be shown, and this is the reason why this is an exact solution of string theory, as a Witten gauge Witten model, and you can see that this is the exact conformity theory, and this is the central charge. You can see from here that this is consistent because when the tension is very big, this guy is not there, and the central charge is 2 because it's a two-dimensional manifold. So if you plug this in the action of the string, this is how the action of the string looks like in this background. So you have this linear dilaton, and then you have this operator here. If you look at it, it looks like a very ugly action because you have an exponential field, exponential potential for the field that mixes with your field, and so on and so on. So, and if you're interested in the spectrum of the theory, you can see that the strings have the following 3 momenta in this manifold. One is the momenta in the radial direction, in the time direction, which eventually is related to the inertia. Also the radial direction, but also the winding number. The winding number is another quantum number that appears in the spectrum. These are the 3 momenta that appears in the spectrum of the theory. You can quantize this theory exactly in terms of the sigma model I mentioned before. So the main tool here will be what is called the Farayev-Samolotchikov conjecture, which is a particular case of T-duality. Showing that this duality is T-duality took a while, but now we understood it well. So this is a particular case of T-duality. This duality I mentioned at the beginning that makes the strings to think that sometimes gravity can be like mimicked by other fields that are not gravity. And the concise realization is the following. This is, if you want, this is the action of the string on this two-dimensional black hole. And if you want to interpret what all these guys means, we already talk about this guy, is the matter that stores the rich tensor for this to be a solution, and it's linear in phi, it's called the dilaton field. And you have this funny operator, very complicated to solve, that if you want, roughly, the interpretation is the one that is responsible for the curvature of the black hole close to the horizon. But that remarkably, Farayev-Samolotchikov in the early 90s, in an unpublished paper, they conjectured something that eventually was proven in 2 different ways, that this is the same to mutilate this semi-infinite cigar and to replace the tip, the atmosphere of black hole, by a manifold that keeps being flat. So there is no deformation of geometry here. It's just flat space-time. But just to resemble the presence of the gravity, you add on it a potential, which means replacing this guy by this guy. Okay? So the curvature of the black hole is not present anymore, but you take it out, you continue the geometry, but you put a potential, exponentially growing potential. This is called a sine-Liouville model, because this is Liouville model and this is sine-Gordon model, so the people call this the sine-Liouville model. But let me talk about this. So according to this conjecture that now we know that is a theorem, these 2 backgrounds are equivalent. This is a kind of puzzling, especially for those that know more about string theory, because the presence of derivative in the operator that creates this curvature means that actually this is a curvature. The fact that we interpret this as a curved space-time comes from the fact that these 2 guys have the 2 derivatives. But here there are no derivatives here. And this is the reason why we don't interpret this as a curvature, but as a potential. Okay? So it relates curvature, gravitons, with the tachyon fields. You can see that this is actually tachyon field that condensates, and this potential, growing potential means that this condensation of tachyon prevents me from going to this region. This is a kind of T-duality. Indeed, you can see that it corresponds to a weak, strong duality. Remember, be reminded of the fact that K was the tension of the string. So when the tension goes to infinity, you should recover the particle limit, particle physics limit, and you see that these 2 guys scale differently. Okay, this is a symptom of the fact that this is a weak regime, strong regime duality. The fact that this is a T-duality that relates manifold with 2 different topologies. If you see the topology of this guy, this is R2 topology, but this guy continues to infinity, so this is a cylinder. So it's a T-duality which is related. It's not the only example, of course, in that sense, but still it's a T-duality map that is relating to different. And it can be seen, and this is one of the ways that people prove this factorial samological conjecture, is the fact that you can see this duality as hereditary property of mirror symmetry. I say hereditary property because mirror symmetry relates the supersymmetric extension of the two theories and not the two theories, but I don't have time to go into it. So another reason is that when the people talk about, especially it was the fashion in 2002, 2003, 2004, there were beautiful papers by Malacena, Moore, and Seiger, other people about, Andy worked on that as well, about the matrix model for the black hole. When the people talk about what is called the Kazakov-Kostov-Kutasov matrix model, it's actually talking about the matrix model you construct with this side, and then at that time, it was a conjecture. Assuming the succeed conjecture, you interpret this matrix model as matrix model describing the black hole. So this turned out to be very useful already 15 years ago to describe the matrix model of the black hole. Another interesting thing is how, due to the fact that the two manifolds have different topology, this winding conservation, the mechanism that produce, for instance, the winding number violation in the two manifolds is totally different. Here it's just because basically a string can slip through the tip of the cigar, but here is the explicit dependence of the dual variable that basically explicitly breaks winding number conservation in the manifold. Another mechanism that is different is the reason why the mechanism that prevents the string from going to a very dangerous zone, which is where the perturbative string theory breaks down, which is a strong coupling regime zone. So here, this part doesn't even exist in the two-dimensional black hole, but here you are extending it. So for the string to be safe from probing this region where the perturbative strings breaks down, the reason why it happens is because you have this penetration wall that doesn't allow to go there. It's like the Wilfing theory for those that know what I'm talking about. So, and you can, I mean, this has been eventually proven, but several years later by the gentleman. So recently there is this paper 1 year ago by Gideon, Isaki, and Kutasov, analyzing the following. They compute the two-point function here. The two-point function gives, it's not exactly that, but from the two-point function you can read the reflection coefficient. Namely, the reflection coefficient tell you basically if I'm very far from the black hole, I throw in a state, what it gets reflected back, basically. So from this you can read as a standard quantum mechanical problem the phase shift. Okay, this guy that goes like, the phase minus one that to which it is proportional the reflection coefficient in the wave packet approximation and scattering process, and then they realize that the two-point function you can compute it either here or here, and you can check explicitly that it's the same. And actually, you find this anomalous phase shift. For doing this, there are two gamma functions. You have to make a Stirling approximation. But eventually, what it means is that when strings have a momentum that is much bigger than the square root of the tension of themselves, so they have very high energy strings when they are vibrating a lot, the strings receive this anomalous phase shift. This anomalous phase shift that tends to 1 when the strings look like particles. So this dependence on the momentum in the two-point function, in the reflection coefficient, is something that doesn't happen when you probe the black hole with the particle physics. So they interpreted this as a symptom that at very high energy, strings see the horizon in some way, a smeared way. Let me focus on the argument. I will not advocate neither in favor or against this argument because I have personal problems to understand the analytic continuation to the Lorentz in this case, but let me revise the argument. The argument is that you can compute the two-point function, but then you can compute the two-point function here, the reflection coefficient here or here, but if you want to interpret it here, it's very natural interpretation. It comes from the integration of a zero mode of one field. And if you think from which region this integral contributes the most, you get that it contributes from the region in which in this side it doesn't exist and it corresponds to the interior of the horizon. So they took this as a symptom of that something is going on with the interior of the horizon at very high energy. The strings kind of prove the horizon somehow inside or something like that. I have a hard time to understand the Lorentzian continuation of this idea, but this is their argument. But apart from this particular application, we can already say that string theory is, I mean, this FCC dual, this dual picture in terms of the dual theory has been useful to understand several things. In particular, the matrix model is an automatic example of its usefulness. So the question is whether, and this is a different question that Izaki, Gideon, and Kutasaw raised recently, and this is what I want to talk about, is whether this idea, this dual picture, can be extended, can be generalized. To what extent we can generalize what we know about this dual picture, this dual way of seeing the black hole, this dual way of interpreting how a string perceive the black hole geometry. And this is the idea. The idea is the generalized FCC duality. Be reminded of what FCC duality means that this curved manifold, strings probing this curved manifold, see the same, feel the same, the results mathematically are the same as a string probing this flat space, but with tachyon potential. Another way of saying this is that there is a duality between the operator that creates this curvature, that produces this curvature in the manifold, this marginal operator, and the marginal operator that gives this tachyon profile. So what this gentleman proposed is that this can be seen as a very particular example of a most general map between states in the two theories, and not only the marginal operator that creates the potentials in the manifold, but all the string states can be mapped in this way. Well, the dots here correspond to some exact RC operators when L is equal to 1, but it is a technicality. So this map between operators is still very remarkable from the string theory point of view, because again, the presence of, let's say for instance, if L is 1, the presence of this derivative means that these are excited states, like graviton state, while here you have tachyons in the background, okay? So even the perturbative spectrum, the two theories are different. So graviton now is not only a black hole, it's similar to a tachyonic background. It's like gravitons in black holes are similar to tachyons in a tachyonic background. That's the generalized state. This is, the evidence for that is just only that these operators have the same spectrum. But actually, this is the only thing that they share, because the rest is totally different. Okay. For instance, they have different winding number. They have winding number 1, and this guy has winding number 0. They have different wave function support. If you take, for instance, the tension of the string to be very large, you will see that the wave function that corresponds to a state here picks up in a very different way. That's why I put this string very far and this string close to the would-be horizon. So the question is whether there is some kind of hyperfine structure of this, namely if this identity at the level of the spectrum can be seen at the level of interactions. And this is what I did. I just compute scattering amplitudes of strings. You can do it at 3 levels at 1 loop. And just compute 2 scattering amplitudes, but put inside operators of the 2 different flavors and see whether they match or not. And indeed, the result is remarkable because there are funny cancellations, but you can see that explicitly they factorize in a way that this can be always absorbed in the normalization. If you want, you are even computing the normalization of the operators and making precise this map. So if you want, this is the conclusion. So you can see that this generalized version of the duality holds at the level of not only the free theory, but also at the level of interactive theory. You can do it explicitly showing scattering amplitudes, at least at 1 loop, and it somehow explains a lot of interconnection between different, if you want, curiosities that were appearing in the literature in the last 15 years. How this operator look like this guy doesn't look like this guy, but if I flip it up, it look like this guy. So this duality explains a lot of connection about these different papers that were going around in the last 15 years, even more. Okay, that's it. Thank you.
We're running a little over time, so I think we have time though for one short question. So that's a short question.
So what about the Lorentzian picture?
That's
Okay.
not a short question.
Yeah, I mean the Lorentzian picture. I mean, let me be concise. The Lorentzian, everything we know of the Lorentzian, not only in the black hole, also in AS3, we take it from the Euclidean case. Okay. We compute in the Euclidean case, and then we assume some kind of analytic extension of the representation of the sigma model and go to the application part. So we we can compute two-point function, we can compute three-point function this way explicitly, but the interpretation of this of this anomalous phase shift, I personally don't understand the Lorentzian interpretation of it. And this is one of the open questions they left in their paper. The first paper I given with this stringy horizon of the 2015, not in the second, the first one, they left this as an open question. It will be interesting to see whether in the Lorentzian extension, this interpretation as an anomalous phase shift still is with this interpretation. I don't think it has been understood well.
So while they're setting up, I'll introduce Carina. So our next speaker is Carina Prunkl. Carina got her bachelor's and master's in physics at the Freie Universität in Berlin, her master's in philosophy of physics at Oxford, and she's now in her final year of her DPhil at Oxford. She works primarily in foundations of quantum statistical mechanics and the role of thermodynamics in quantum theory. That has very naturally led her to work on black hole thermodynamics. And I guess I'll say, in sum, that like any self-respecting German, she speaks better English than pretty much all the native speakers in this room. So,
It's not true.
I got it.
That one? Well, almost, except for the well, I mean, parts of the slide was missing. Well, oh, it's incomplete.
We're just on a panel.
Okay, good. Perfect. Well, thank you, Eric, for introducing me, and thank you for inviting me. It's an honor to speak here. Yeah, as Eric said, my work is on the conceptual foundations of entropy, so dealing with black holes came quite naturally. And my talk today is going to be about whether we should consider black holes to be actually genuine thermodynamic objects with a well-defined thermodynamic entropy, or whether we need to rely on information theoretic arguments as some of the literature suggests. So I want to begin with an opening quote by Wald as a kind of a motivation of why we should worry about black hole entropy. So Wald writes, I believe that in order to gain a better understanding of the degrees of freedom responsible for black hole entropy, it would be necessary to achieve a deeper understanding of the notion of entropy itself. Even in flat spacetime, there is far from universal agreement as to the meaning of entropy, particularly in quantum theory, and as to the nature of the second law of thermodynamics. The situation in general relativity is considerably murkier. It seems likely that a new conceptual framework will be required in order to have a proper understanding of entropy in quantum gravitational physics. And that entropy is this iffy topic. It's not a new thing. There's this famous anecdote about von Neumann and Shannon, where Shannon came to von Neumann and he asked, like, what should I call this newly discovered entity that he had? And von Neumann said, oh, just call it entropy first, because it's very similar to the statistical mechanical entropy. But second, if you ever get into an argument, because nobody knows what entropy means anyways, you always win it. So the big question then is, what is entropy? And it seems, it's a big question. There. And it seems that there are just very different opinions about what entropy could be. The most uncontroversial one is the phenomenological entropy, where entropy is taken to be a quantifier for the amount of heat exchanged during a reversible process. But it gets a bit murkier when we come to the statistical mechanical generalizations of entropy, where it's then unclear whether entropy refers to some sort of disorder that defines an arrow of time, or whether it refers to the lack of information of an observer, or whether it's actually a property of the system itself. So this is my roadmap for today. I'm first going to talk a bit more about entropy and the problems we have generalizing it to statistical mechanics, before quickly repeating the laws of black hole thermodynamics and why current arguments that try to establish the analogy between the black hole entropy and between the thermodynamic entropy and the black hole entropy are problematic. Before, I'm going to suggest a different approach, which is going to be based on coupling the black hole to a photon gas and basically letting it undergo a Carnot cycle. But we'll come to this later. So the phenomenological origins of entropy can be found with Clausius and Kelvin. So the famous Clausius principle says it is impossible to perform a cyclic process which has no other result than that heat is absorbed from a reservoir with a low temperature and emitted into a reservoir with a higher temperature. And the Kelvin principle, often said to be equivalent to the Clausius principle, which states it is impossible to perform a cyclic process with no other result than that heat is absorbed from a reservoir and work is performed. And I want to draw special attention to the fact that they are both talking about cycles, because if we don't require our system to return to its original state, it doesn't seem to be all too problematic to come up with a setup where we can transfer heat from a reservoir at a lower temperature to a reservoir at a higher temperature. So the phenomenological entropy is here at the top. I'm sure you're all familiar with it, with equality given for reversible processes. And then there are a few suggestions for statistical generalizations. But one of them is the so-called Boltzmann entropy, where the entropy is given by the logarithm of the phase space volume of the macrostate the microstate of the system is in. The advantage of the Boltzmann entropy is of defining entropy this way, that since each microstate is assigned a unique macrostate, the entropy will always be a property of the system itself. Another advantage is that it's mostly increasing, mostly because it's not always increasing. Sometimes it can be decreasing, which differs from what we would expect from phenomenological entropy. So the other and more popular amongst physicists by far is the Gibbs entropy and its quantum statistical generalization, the von Neumann entropy, where the entropy is given as a functional on phase space. As a functional of the probability distribution over phase space, and right. So all of these, it's hard to see. All of these entropies pick up certain features we would expect from the thermodynamic entropy, but they all fail at recovering fully what we take thermodynamic entropy to be. And I want to pick out a particular example, a so-called information theoretic interpretation of the Gibbs entropy as it is usually used for arguments about black hole entropy, and I want to just briefly show why it's problematic to consider an information theoretic approach to the Gibbs entropy. So, so this quote by Bekenstein kind of motivates how an information theorist would see entropy. He writes, "The second law of thermodynamics is easily understood in the context of information theory. The entropy of an evolving thermodynamic system increases due to the gradual loss of information, which is a consequence of the washing out of the initial conditions." But it's actually not so easy, because given that so in entropy, in the Gibbs entropy, the equilibrium system is at equilibrium if the probability distribution is the equilibrium distribution. So, but now if the probability distribution is merely an expression of our ignorance about the underlying microstate the system is in, then the equilibrium is not a property of the system itself, but is also a property of the observer and the ignorance of the observer. Another problem is that the Gibbs entropy remains constant under the Hamiltonian flows. So this guarantees that the entropy is never decreasing, but it also means that the entropy is never increasing, as opposed to the phenomenological entropy, which can increase, which does increase. Usually justifications usually appear usually we use coarse graining to justify this increase, but there's always a problem with justifying this coarse graining, like motivating this coarse graining physically. And in particular, if we take the coarse graining simply to be,
Yeah, so I'm not sure where to ask this question because you've sort of touched on it at several points, but I guess I would disagree with the opening quote by Wald. I don't know if you're agreeing with it or not, but it's sort of being used as motivation for the discussion. I don't see any evidence that, all these different kinds of entropies and the relation, statistical entropies and the relation to thermodynamic entropy, it's certainly an interesting subject and an interesting discussion, but I don't see any evidence that it is not orthogonal to the question of black hole entropy. I would say that the question of black holes can be understood as I would hypothesize that black holes can be understood as statistical systems, just like a box of molecules or a box of gas. I think Wald's quote might have been more appropriate 10 years earlier, before we had found examples in string theory where it was demonstrated that we can understand it as a statistical system. Then we might have thought that we needed to think about things differently in order to understand black hole entropy. But we certainly found examples in string theory. We used the first one, the Boltzmann entropy, and it agreed, and we can think about it as a statistical thermodynamic system like any other kind of system. And I think that is the whole goal of understanding black hole entropy, is that it shouldn't be special. It should be just like every other kind of entropy. And yes, you can study it as an ensemble in the Gibbs entropy or the von Neumann entropy or the Boltzmann entropy, but there's nothing different about black holes in that sense. So I don't see now, given the successes that we've had in various examples, I don't see any evidence that in order to understand black hole entropy, we need a better understanding of ordinary entropy. We certainly need a better understanding of ordinary entropy for many ordinary applications where people are discussing it, but I don't see what the evidence is that black holes are special in this regard.
Well, I wonder whether this better belongs into the discussion after I've said everything. Maybe a brief reply is that I think it's far from decided on what the black hole or how to interpret the black hole entropy. You say it's a statistical entropy, but then which statistical entropy are you?
You can ask that question about this thing. What's the entropy of the water here? Okay. Right. We could have a long discussion about the different kinds of entropies you could associate with that.
Exactly. So my point is more that maybe given that given that we can't even decide on which statistical entropy is a relevant entropy, we should start with a phenomenological entropy, because like the reason why we have statistical entropies in the first place, it comes from having a phenomenological entropy. Like it's now this whole field in itself, but why we have it is like the origin is in thermodynamics. But maybe this is better. This is better a discussion we should have over pizza, and so I can I can continue with it. Right. Anyway, so my whole point of this discussion, like apologies if it seemed to be different, is that the identification of a statistical entropy with a thermodynamic entropy is non-trivial, if we desire to do so at all. So I don't want to dwell on this much longer. I just want to briefly revise the black hole, the laws of black hole thermodynamics. I guess now that I've been stolen a few minutes, I'm just going to briefly to just put them out here and I guess you're all familiar with the equivalent laws in thermodynamics. I'm going to be focusing on the generalized second law, which states that the entropy outside of the black hole, the change of the entropy outside of the black hole, plus the change of the area of the horizon of the black hole, has to be non-decreasing, in analogy with the thermodynamic second law, where the entropy is supposed to be non-decreasing. So there are, broadly speaking, two classes of arguments that try to establish a black hole entropy. One of them are arguments that appeal to the similarity in the laws of black hole mechanics and the laws of thermodynamics. So common arguments are the energy change related to the area change in black holes is exactly the same, has exactly the same relation as the energy change related to the change in entropy in a thermodynamic system. Then another one is like if we merge two black holes, it's possible to extract work from them. Just as if we have two thermodynamic systems at different temperature, it's possible to extract work. And the third one is that if the entropy of a thermodynamic system increases, means that there is an information loss, and just in the black hole case, if information is lost because an object crosses the horizon, then this should coincide with the area increase. Then there are other arguments which appeal to the preservation of the second law. So those arguments basically state that either we identify the surface area of the black hole with the entropy, or we are going to have a violation of the second law on the outside of the black hole, given that the interior of the black hole is causally isolated. Yes. So there are some problems with those approaches. One of them is that if we appeal to the similarity in the laws, and we can establish at most an analogy but not an identity of surface area and entropy, for example. In particularly, those similarities are, it's a bit cherry picking, because there are some things that are not easily, that are not similar. For example, surface gravity is a non-intensive entity, whereas temperature is an intensive entity. And the other, so this is fairly obvious that appealing to analogies, to similarity can at most establish an analogy but not an identity. The other problem is a bit more subtle. So with approaches that appeal to the preservation of the second law, it seems that there's so there you go, right? Either we identify the surface area with the entropy, or the second law is violated, but there doesn't seem to be a physical justification for why we should be able to treat black holes as thermodynamic objects in the first place. And if you can find such justifications, they usually appeal to statistical mechanics, and they mix statistical mechanical and thermodynamical concepts in a way that is problematic, as we saw earlier, since it's not straightforward whether statistical mechanical entropies refer to the same thing as the thermodynamic entropy. The third point is that since we lack a detailed knowledge of the underlying mechanics in a black hole, then it's not business as usual to find a statistical mechanical entropy. So what we want to do, what we did in Oxford, so this joint work with Chris Simpson and O. Moroni, is that we wanted to take a step back from all statistical arguments and see whether we can find that black holes are thermodynamic just by appealing to phenomenological thermodynamic arguments as much as possible. So the idea is that we couple the black hole with an ordinary thermodynamic system, such as a photon gas. And the idea is that if we couple a black hole, if we couple something that we're not sure what it is with a thermodynamic system, and both of them together act like a thermodynamic system, then we have reasons to believe that they are thermodynamic systems. But of course, it's not so easy since black holes have negative heat capacities. So one of the big questions is whether we can construct stable equilibrium states. How much time do I have?
You have 10 minutes.
I think I should be fine. And if we have whether we can construct a Carnot cycle, which is pretty. But once we have this, it's pretty straightforward to construct a Carnot cycle. And then, of course, what is the thermodynamic entropy that we get out of these considerations? So as I said, in order to establish, so we take the black hole and we couple it to a photon gas and we put it into a big box. And we assign the total system an energy which is given by the energy of the photon gas and the energy of the black hole. And we solve this equation for the temperature of the photon gas, temperature of the black hole, where we assume that the temperature, so this is one of the big assumptions, we assume that that Hawking's result is valid and that temperature of the black hole is inversely proportional to its mass.
Do you allow the black hole to heat up the photons, to accrete?
Sorry?
Do you allow the black hole to accrete photons?
I don't need to. Well, wait a second. So one of the big so the equilibrium condition is then given that the temperature of the gas and the temperature of the black hole are the same. And if we solve this equation, then we get this quantic equation, which is not exactly solvable, but we find that there is an upper, for a given energy, there is an upper bound for the box size, which is where beta is a constant made of alpha and gamma. So this is not phenomenologically motivated, but physically motivated. Is that we want our black hole the equilibrium to be stable, because otherwise we would get runaway. Is this a hand? No. Because otherwise we would get runaway processes due to the negative heat capacity of the black hole, and it turns out that we can find stable equilibrium states if the mass of the black hole is smaller than 4/5 of the total mass. Okay, so here is now our very simplified model of the black hole Carnot cycle. We start out with a black hole in a box coupled to the photon gas, and so the first step is an isothermal expansion, where we see that the black hole mass doesn't change because the temperature is the same. Second step is an adiabatic expansion, where there is no heat exchange with the environment, but since the temperature changes, now the black hole will also change. And then we just finish the Carnot cycle. We have the adiabatic compression and the isothermal compression. Isothermal compression and then the adiabatic compression. And it turns out that this system is just a well-behaved thermodynamic system where we get the usual Carnot efficiency. So the main, so when we look at the
Sorry, I know you're pressed for time, but I didn't understand
yeah,
that.
sorry, what?
So you're putting the black hole in a photon bath, right?
Mhm.
And they both have temperatures, and you're saying you can find a stable equilibrium as long as the energy content of the photon gas is less than a fifth of the energy content of the total.
Sorry,
system.
and so the box has to be small enough as well. And the
Okay, that was
equilibrium
your
is stable, and
previous
it's,
slide.
yes,
Yeah.
exactly.
So then, what are these four steps that we,
Okay,
so in our understanding, there's going to be a steady interaction between a black hole and a photon gas surrounding it. What makes it break down into four distinct types of, like, isothermal and?
this is just like a normal Carnot engine, yeah. What we do is we let the gas expand and then we compress it afterwards as well. So it's just like
So
the
you
normal
are
Carnot engine.
imposing these
I
on
am
the box?
imposing. Yes.
But one thing that you didn't mention is, I mean, photons can enter the black hole and disappear there.
Yeah.
So that is not included in your description.
Well, I have the
That's
Hawking
what the
radiation.
The equilibrium is equilibrium. It means what goes in is compensated by what
The rate of incoming
Well, I'm not
photons
sure if
is
the rate of evaporation of the black hole compensates exactly for
That
that
is what
ratio.
equilibrium.
That's for
So
equilibrium.
that's
the
the
equilibrium.
That's
setup.
exactly the definition.
So that's what gives this box size
Yeah.
constraints,
Right.
like the energy, okay, yeah, okay, so.
You're
The
not
reason
just
it can't
temperature.
happen in an arbitrary system is the rate of absorbing has to offset the rate of Hawking radiation.
You're doing
Okay.
everything quasi-statically and
Okay,
in
yeah.
little
And
infinite
And
small
the, yeah,
steps, and
so
so there's
the
equilibration.
equilibrium conditions were necessary to make sure that we can have these quasi-static movements that we have in the normal Carnot cycle as well, which otherwise we wouldn't.
And then you are doing these
I am
arbitrary
doing these
things
things,
on the,
yes.
on the
I'm
box.
doing a Carnot
Okay.
cycle.
Okay.
I guess, just before you proceed, those black hole circles are changing in size. Is that supposed to represent area?
Yes.
So the area is really shrinking between stage 3 and 4. 3 and back
Yes.
to 1. And that is Hawking evaporation
Yes.
at that point. Okay.
So we take the adiabats to be the paths of no heat exchange with the environment. We know that the adiabats of a photon gas are different from the ones of our coupled system. So this means that during this adiabatic expansion stage, there must have been a flux of energy from the photon gas into the black hole, because the whole total system is isolated and energy is conserved. So it seems reasonable then so this is also, I mean, yeah, it might become clear now that it's like this is also a sort of like compensation approach, because we require the total entropy of the box to be unchanging, and the entropy of the black hole and the radiation gas to be additive, which then means that if we calculate the entropy change in the photon gas during the adiabatic expansion, and then we insert the conditions that we got for the adiabatic relations of the coupled system, then we obtain an expression which equals the Wittgenstein-Hawking expression for entropy. Okay, so I have discussed why we should consider some of the current arguments for the identity between black hole entropy and thermodynamic entropy as problematic. And I've also shown that coupled to a photon gas, when we couple black holes to a photon gas, then there exist stable equilibrium states. Then black holes are indeed genuine, well-behaved thermodynamic objects. And in particular, if we measure the entropy difference, we recover the usual expression for the Wittgenstein-Hawking entropy. Now, there are of course some caveats, like this is a highly idealized model, as you might have noticed. So for example, when we have a pure black hole, it seems to be difficult to establish equilibrium with a photon gas in the first place. Plus, we've been only discussing photons, not other particles. And yes, and think there was something else, but I forgot. But anyways, it's a very simplified model, so you have to take it with a grain of salt. And yes. Oops. Thank you for your attention.
We have time for one or two short questions. Ali?
So I was missing one thing in your description. You didn't have gravity, so there is gravitational potential.
That was the third one. That was the third one. I was.
So
just
even both in the Newtonian regime and in Einstein's theory, the photons are redshift. I mean, there is gravitational potential there, and that adds another term in your equation.
Yes.
So what about that? Doesn't it change the arithmetics?
I don't know. I haven't calculated it through. But yeah, no, we have completely ignored the effect of gravity on the photons in this model.
I see. Is it justified?
Yeah,
So
I wonder.
how big is
I
your
mean,
box?
the box is large enough. It seems to be that the large part of the photons is going to be fairly unaffected by gravity. So.
If you have a really, really, really bit large box and a really, really, really large black hole, the surface gravity is going to be really, really, really weak.
No, but the point is the temperature is set by the temperature of the black hole. So you know the energy density of the radiation, right? But then the question is how much mass you put in the radiation. If the box needs to be big enough, and that could change gravity as well. That's one.
Yeah,
Because the
fair point,
photons
yeah.
may collapse to a black hole. Or something.
So you kind of just mentioned it in passing. Black holes have negative specific heat.
Yeah.
Does that have any effect at all in your Carnot cycle?
No, the Carnot cycle is.
This works like in
the
normal
Carnot-
thermodynamics.
But that's only because it does. The heavy lifting was done by establishing the equilibrium conditions, basically, and that's where the negative heat capacity is problematic.
Right. If you make the box too big, you can't find the equilibrium. Right.
Yes.
Once
for
you've
example.
got the equilibrium, you're saying the fact that it's negative specific heat is not.
Or if the black hole, or if the black hole has too much energy for the box as well. Yeah.
But that's a feature of gravity. Negative heat capacity is not black hole, it's gravity.
Right. But I was wondering, because the Carnot cycle or all of these theorems you started with, what they say is that the heat engine will take heat from a higher temperature and deliver it to a lower temperature and will get work out of it, right? You can't do it the other way, right? You can't take heat from the lower temperature and put it in the higher temperature.
And get work
Engine
out of
won't
it.
work then, So I presume this guy will still satisfy that theorem, that you can only, the way the work.
Yes, so that's the
Comes
reason. Yeah. Oops, sorry. So that's the reason why we chose the Carnot cycle, because it's the most primitive example you can come up, and it's the Carnot example. That before the formulation of the second law, this was basically paving the.
Very good.
So we have time for one last quick question.
Yeah, just to follow up on Maciek's question. If you have a negative heat capacity, usually it's an unstable system, but you also have a photon gas, so maybe the total heat capacity is positive.
That's good.
Yeah.
That's her equilibrium.
That's good.
Yeah, that's her
why you're
stability.
And that's why we need. Well, that's what we need, because if we put it in touch with the infinite heat bath, then otherwise it would be completely unstable.
That's good.
Let's thank Carina again.
Great. Well, so our last speaker today is Maciek, who's visiting us, and he's one of the newest BHI postdocs, also with a focus on EHT work. So he'll be joining, I guess, probably the first of the new bunch to join. He'll be here permanently in May or thereabouts. So lots of time to answer questions in the future.
We also have a talk at 3 p.m. by another future postdoc.
Yeah, which I think you said for the whole group. Yeah. So lots of.
That's in the night. Yao, is it downstairs?
Yeah, downstairs.
Downstairs at 3 p.m. If anyone is interested.
Okay, we should be done in time. So I'll give you a 5-minute warning.
Nobody's honest.
No signal.
try with this one again. We tried this one before and it didn't work. Oh, now I can see it here. Maybe it will be fine. To change slides or okay, that's fine. I'll use that. Well, okay. Hello everyone. I'm very glad to be here. Thank you for squeezing my short talk into this session on quite a short notice on my way back to Warsaw from California. So I would like to make it really full screen, but I'm afraid that if I touch something else, it will break up. I'll take a risk. Maybe F11. I broke it. Wait a second, something is happening. Okay, let's not insist on the full screen. Yes, okay, let's do it in that way. Okay, so I didn't provide the title for my talk because I was overthinking it during last couple of days. I wanted something that would catch attention, so I came up with the title, Are We Being Honest? But then I decided that in that case some subtitle would be necessary. So then, what do I mean? Are we being honest when we are using MHD equations to investigate the accretion flows in systems like Sagittarius A star? But then I was overthinking it even more, and I added a second subtitle to explain fully what my talk is all about. The plasma is most certainly collisionless in systems such as Sagittarius A star. So why are we doing MHD? So this is what we are doing. Many people do that. This is actually me doing this particular simulation. So this is magnetohydrodynamics, put in general relativistic background with radiation. It's radiated 3D simulation. But, well, if you look at the parameters, you will probably know what kind of system I want to simulate in this particular run. These are parameters of M87. This is low density. This very low mass accretion rate means low density in the flow. If you take a look at the temperature distribution during this simulation, characteristic temperature for this kind of flows, advection dominated accretion flows, you see that it's a huge temperature. This is, probably you can see, but it's more than 10 to 11 Kelvin. So it's very hot and not very dense. So now let's recall when we are allowed to use MHD equations. So where are the MHD equations valid? Well, we need to fulfill a couple of conditions. One of these conditions would be that the characteristic length in our system is larger than a couple of radiuses connected to the microphysics of it all. In particular, Larmor length means just this zero radius, and this tells you basically you don't want the gas to be too hot, so it can notice the magnetic field. If the electrons are traveling very fast, you cannot deflect them much with magnetic field. Magnetic field will not really tell the electrons how to behave. And it turns out that in the systems that we are simulating in this accretion flows, Larmor length and mean free path are typically, they can be much larger than the system.
Sorry, why is that? Isn't the force proportional to the velocity?
Excuse me?
Isn't the force proportional to velocity? F equals QV cross
Right,
B.
but then
Why is it that when they're moving fast, they don't see the magnetic field?
Well, the radius will be larger. All I mean by that is that this zero radius will be larger, for larger velocity. So there is magnetic field, and there is an electron running. The faster it runs, the larger is the radius of the circle that it will make. So basically, if it's very fast, then you don't deflect it so much. So by that I mean that magnetic field does not really contribute tremendously to the behavior of this particle. System time scales. We also need to establish that the characteristic time in which our system is changing is much larger than the time for collisions. I will be talking more about collisions. I will explain in details what do I mean in here. There is this kind of condition very often put in textbooks, so for the sake of completeness I put this one as well, the common flow velocity for all the species. So collisional coupling is only efficient if the material is sufficiently dense, if the medium is dense, so we have enough particles to interact, and not too hard, so the particles can bother to notice each other while passing by. So if you do the math, if you try to evaluate the parameters of the flow that we are simulating with MHD equation, it turns out that it's rather collisionless. It's in principle, you violate both of the first conditions. That for sure. You simply violate that. You should not, from this criterion, be using magnetohydrodynamics. It's simply not fluid. It's a bunch of particles that are not colliding, not interacting enough to behave like a fluid. One can even find this kind of criterion that was found many years ago from the viscous disk theory. This is V alpha, the famous viscosity, and this is the condition from simple theory when you can call your flow fluid flow, not a bunch of particles. So this alpha, let's say, is 0.01, so the square gives you 10 to minus 4. 10 to minus 4 of the Eddington accretion rate. It's still 2 orders of magnitude more than the accretion rate of M87, and like 4 orders of magnitude more than the Sagittarius A star mass accretion rate. So we violated terribly. Why are we doing MHD? Let's take a closer look at this collision. So this is some rather nasty formula to tell you how much energy is exchanged between ions and electrons. It has simple dependence of density. Both of these n are densities, so it's density squared, and rather complicated dependence on temperatures. There are some nasty vessels of second kind and 0, first and second order screening our temperatures. Thetas are dimensionless temperatures. If you plot it, it will be easier to see what is this dependence. This is for fixed density, because the dependence on density we can imagine quite easily, and to imagine all those vessels in your head is not that simple. But you can see from this plot, this is logarithmic scale, so it spans 12 orders of magnitude, depending on the solely on temperatures of ions and electrons. You can see that it's not even linear. If the ion is like 10 to 9 kelvins, it's more happy to hit your electrons. So this dependence is not trivial. By the way, it's not like it's just ions and electrons as two species that we should care about. It's like there are groups of ions, groups of electrons. There's one gang of electrons.
If we completely ignore all collisions, is it then like a pressureless dust? Is that?
It's a kinetic theory. This is statistical gas mechanics.
And there's no parameter in the MHD equations that extrapolates between?
Well, I will tell a little more. I will comment on how you get MHD from the kinetic equations. So I would postpone answering until a couple of minutes later. So, oh my God, so quick. Well, okay, I will just skip some material if necessary. So it's not only that we have to take care about our electrons in exchanging energy with ions and whether they have enough time to do that. It's also electrons with electrons. There is no reason why we couldn't have a group of electrons behaving according to one energy distribution, another group of electrons behaving according to another energy distribution. But it turns out that, well, if you consider energy exchange in between electrons and in between ions, you basically have the same nasty stuff in here. You get a different factor there. So this proportion is like that. So this is 1 over 2000. This is 1 over 40 roughly. This is 1. So you can say that 1 is already a lot. 1 over 40 is, depending on your choice, a lot or not so much. And you can say that 1 over 2000 is perhaps not so much.
But you know that in the laboratory, when people put plasmas in the laboratory, most of the energy is transferred through wave-particle interaction, not?
I'm getting to that. So now we're looking just to the collisions, because this is how textbooks define the validity of MHD. Do we have enough collisions to call this stuff a fluid? Well, okay, so we jump forward. Of course, people were doing things in more general way than MHD. The more general theory is the kinetic theory of gas. And there have been constant progress in the field and in numerical aspects of this field for many, many years. But I will jump to the state of the art because I have less than 5 minutes right now. So state of the art, it's like 4 months, so maybe not anymore, but hopefully recent enough. So let's take a look at this particular paper. Let's see what those people did. So they performed in the framework of the kinetic gas theory 3D simulations of which are showing the magnetorotational turbulence and magnetorotational dynamo effect. So apparently now you are able to do that in the numerical framework. It costs 6 million CPU hours, and they were able to do a single simulation. But of course, this simulation is very important because the results will show us whether our MHD ideas are for some magical reason relevant. Well, and by saying that they do kinetic theory, it's not so good. They actually assume that this electron and electron coupling is working fine. So they actually have electron fluid, but they do have kinetic ions, and of course coupling between ions and electrons is not fluid-like. Right, and they have no relativity, but this is not really interesting part of this research. So then they give a very detailed explanation of all the differences between this shearing box simulation in the kinetic framework and the MHD framework. But in particular, this is the energy spectrum of their ions, and this is the fit from Maxwell distribution. It's not Maxwellian. They have some high energy ions. So this is one of the interesting things. They give a lot of similarities, and they vaguely describe in that paper that this is really a negative result paper, meaning that they actually discovered that, well, people were expecting that. They have seen that for some reason, MHD works actually quite fine. And I had pleasure to talk to two of the authors of this paper very recently in California. And in private communication, they speak more freely, and they actually acknowledged that the difference between these kinetic computations and magnetohydrodynamical computations are more similar than many purely MHD simulations done on different resolutions. So this should be really disturbing, and this does disturb many people doing magnetohydrodynamics, dependence of the properties of the flow solely on the resolution. Okay, I will skip most of the second part. I overestimated, but I just need a minute to wrap it up. Apparently there is a mechanism that is providing MHD with sufficiently good results. I will, two slides. So I said that I would comment on the relation between MHD and the kinetic theory. So kinetic theory is really Boltzmann equation, or when you couple it with Maxwell equation, this gives you Vlasov equation. And basically, if this is all written in the phase space, so in 6 dimensions, free space, free for the momentum. If you integrate it
what's alpha?
Sorry, alpha is the index of species. It's E for electrons and I for ions. This is just that. And you have this collision like term. So basically what we want to say, to go into the fluid regime, is to say that this guy is so strong that it had time to operate, and it resulted in a stationary state, meaning that you don't have time derivative here anymore. This guy did his job, and now it's 0. So this is when we this is a part of saying when we can use the fluid approximation. So I'm really finished. There is the other guy in here. And apparently there are some mechanisms that can act effectively as these collisions. In this case, this is interaction not of particle and particle bouncing into one another, but wave with the particle. So I will jump straight to the conclusions, and I will not show any of that. I did it so quick that you didn't even see what I had there. So formally, when you take the criterion based on the collisionality, MHD is invalid for ADAF-like flows. And there is no way around that. We should formulate our excuses in well, consistent way. We cannot say that somehow by average these particles interact. It's not the interaction of particles and particles. So, nevertheless, some mechanisms force fluid to be qualitatively force this bunch of particles to qualitatively behave as a fluid. But simulations like these most up-to-date simulations that I just discussed cannot get what we observers, we astrophysicists really want. And we don't want the overall dynamics of the system, which, okay, is fine with standard MHD. We want the thermodynamics of electrons. So the part of my talk that I will not show because I will finish in 30.
You can't say it either because we have to end so people can get down to the 3 o'clock talk.
Yeah.
So you can't
It's
say what you're not going to
15
talk about.
seconds. It's 15 seconds.
Okay.
So one simpler thing than jumping straight to kinetic simulations is just distinguishing between temperatures of electrons and ions. So this is breaking this first of these 3 assumptions. There was coupling between electrons, ions, and ions, electrons. And this is part of the work that I've been involved in with people here. And that's the conclusion there.
No time for
I'm sorry for stretching.
But there will be time for questions, remember, at pizza at 4:30, so please show up. And we'll be here next year, so you can have everyone questions.
Good, how are you doing?